we're going to try this again. Simple pendulums. Okay, and I want to show you why the period of a pendulum equals 2 pi times the square root of L over G. Why is this true? I just kind of stated it last time. That's all the time we had. So I really want to at least justify it. So we're going to do that by reviewing a little bit. We have a mass spring system. And here's my mass. Here's my spring. It's got a spring constant of K. When it's right here, there's no force from the spring. But if you come out here to A, that's our amplitude, or if we squished it into negative A, you're going to feel the force of that spring. In fact, if we pull this thing out like this and release it, this thing will oscillate back and forth forever. And last time, well, first of all, if I draw a Freebody diagram of this guy, I've got gravity. It's trying to pull it down. We got a normal force supporting the gravity, but if we're over here somewhere, we've got the spring force, which is negative kx. That's Hooke's law. The force of a spring is equal to negative kx. Negative meaning the opposite of the direction of my displacement. If I displace this to the right, the force of the spring is to the left. If I compress this thing to the left, so we have negative x, the force is to the right. So this negative just means in the opposite direction as your position x. And when we said that, we said, well, the net force equals ma. What is the net force? That's negative kx equals ma. We solved for a. A equals negative k over m times x. And this right here, last time we discussed that this is the angular frequency of the system squared. So that omega squared equals the square root of k over m. I'm sorry. Omega squared equals k over m. So the angular frequency equals the square root of k over m. And so when I did a conversion to period, this equals 2 pi times the square root of m over k. Right? Because period equals 2 pi over the angular frequency. Look that up if you don't remember that particular formula. So this is what we did to a mass spring system. Now I'm going to try to do the same analysis for a simple pendulum. But it's going to be a little different. Simple pendulum, as we said before, is just a little weight on a string. Has a mass m. We deflected out a small angle. We call this theta. So now it's right here. And we're going to say that the string has a length of L. And this thing is going to rock back and forth like this. And what we're going to show is that if the angle is small, this is very, very close to being simple harmonic motion. Watch. I'm going to draw a free body diagram of this guy. Well, here's my tension force. Here's gravity, mg. Now, if I took a component of gravity, if I extend this out, if this is theta here, this is theta. And if I break the gravity into a component that is both radial and tangential, well, this tangential component, this is the component of the gravity force that's trying to pull it back towards the center. This is the net force, this mg sine theta, right? It's the opposite. So we're going to say this. We're going to say that the net force is equal to ma, but of course we're dealing with the tangential force, the tangential acceleration. Well, that's going to be equal to mg sine theta. Well, the masses cancel, and I'm going to solve for acceleration here. Acceleration equals g sine theta. Oh, but I left something out. Notice that the force is always in the opposite direction as my displacement. If I pull this thing to the left, the force is to the right. If I pull this thing to the right, the force is trying to pull it to the left. So we indicate that by putting a negative sign on there, just means it's in the opposite direction. Now this equation does not look like this equation yet. But I'm going to do a little trick, and I have to do it quick because I only got like 6 minutes left. I'm going to divide by L, both sides by L. Why? Because I can. Watch. A over L, this is the tangential acceleration, equals negative G over L times sine theta. Well, what is this? What is the tangential acceleration divided by? Well, notice that L is the radius of this thing. It's the angular acceleration. Oh, now we got angular acceleration equals negative G over L times the sine of theta. Wow, this is really getting close. That is acceleration, angular acceleration, equals negative constant stuff, but here we have x, here we have sine theta. If this was theta instead of sine theta, we could do this. I mean, we could make it, say it's simple harmonic. Well, there's a little trick called the small angle approximation. Now, normally I do a whole lesson on this, but today's not the day to do that. Because we had... Okay, now, take a look at that. What is this telling us? What if theta was 30 degrees? Well, change theta to radians. How do you divide what? There's 360 degrees in 2 pi radians, so you do the conversion factor. Trust me, 30 degrees in radians is 0.52360. Take the sine of that, make sure your calculator's in radians, take the sine of it and you get 0.5. Right? We all know the sine of 30 is 0.5. Hey, notice that theta and sine theta, they're pretty close. Only 4.7% different. Well, what if I had a smaller angle? If I took 20 degrees, converted that to radians, and then looked at sine theta, oh, look, only 2% different. Well, what if I had 15 degrees and change that to radians and take the sine of it? Oh, the answer is almost exactly the same. In fact, if you go less than 10%, if you keep your angle really small, then theta and sine theta become the same number. And that's called the small angle approximation. So if thank you. Zoom out. If theta is small, less than 10 degrees, and it can be up to 30 degrees, and it's still pretty close, then theta is approximately equal to sine theta. Well, what does that mean? That means that we can say that if your angle is small, you can say that your angular acceleration is equal to negative G over L times theta. Instead of the sine theta here, we can approximate it with just theta. Now, theta has to be in radians. This only works for radians. But look at this. Well, this should be approximately equal to that if the angle is really small. Well, look at this. This has the same mathematical structure as this. So therefore, it approximates simple harmonic motion. And what's the angular frequency? Well, the angular frequency squared is equal to G over L. Let me zoom out. Well, this means that omega is equal to the square root of G over L, which means that the period is equal to 2 pi times the square root of L over G. Now, this is for small angles. If you try making it like big, huge swings where the angle goes all the way up to 40, 50, 60 degrees, this is not going to work. But if you keep the angle of the swing like, really small, then this works really well. So, but it's an approximation. It's an approximation because, and this, by the way, this is what physicists do all the time. They make approximations. So this is why pendulums can be approximate simple harmonic motion, whereas mass spring systems are perfectly, perfectly described by simple harmonic motion. I think I'm out as far as I can go. No, there we go. Okay. Well, that's as good as I'm going to get this year. That is all.